assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
So this problem involves two different particles that are both undergoing simple harmonic motion over a distance of length a, which we don't know exactly what that value is, but we do know that both of the particles have a period of 1.5 seconds. We also know then that our amplitude for these particles is going to be a divided by 2, because if the whole length is a, then the amplitude is going to be half of that value. And we also know that they have a phase difference of pi over 6. And we're being asked to figure out where they are in relation to each other in terms of a, 0.5 seconds after one of the particles leaves the end of its path. So the first thing that we have to do is kind of create the coordinates for these two particles. So for particle 1, the displacement of that particle is going to be a over 2 times cosine of its omega t. It's omega time. Because it's at the end, it's 0.5 seconds after it left, we can have that be our 0, so we don't have to worry about our phase constant. Whereas our second particle, which is slightly out of phase with our first, is going to have a position of a over 2 cosine omega t plus phi, its phase constant. And in this case, its phase constant, we can substitute the phi out for pi over 6 because that is their phase difference. At this point, we're going to have to think about doing some substituting of terms here based upon the information that we have. So for one thing, we know that we can take omega and actually replace omega with 2 pi f. And while we don't have the frequency from this problem, we can also write frequency in terms of period, because period is 1 divided by frequency, or we could say frequency is 1 divided by the period. So substituting this portion in for our f, we now have omega equals 2 pi over the period. So we can take this portion and actually replace our omegas from our original position functions. So our new functions are the position of x1, our first particle, is going to be a over 2 cosine of 2 pi times our time over our period. And our position for 2 is going to be a over 2 cosine 2 pi times our time over our period plus pi over 6. And now we can actually substitute in our known values of our period and our time, because we know that our time is 0.5 seconds, because we're trying to figure out how far away they are from each other 0.5 seconds after restarting one of the cycles. So putting in my known values, I will have for x1, I will have a over 2 cosine of 2 pi times 0.5 divided by 1.5, because my period is 1.5, which will give me a value of negative 0.25a. For x2, I have a over 2 cosine 2 pi times 0.5 divided by 1.5 plus pi over 6. and that gives me a value of negative 0.43a. So those are their positions, but I want to know how far apart they are in relation to each other. So my delta x, my delta position, is going to be my x1 minus my x2. So it'll be negative 0.25a minus negative 0.43a, giving me a total difference in displacement of 0.18a. So that is my final answer for part A. Okay, now for part B, they are asking whether or not the two particles are moving in the same direction, if they're towards each other or away from each other. So for this, we need to look at our velocity equation, where velocity equals negative omega times amplitude sine of omega time plus phi. So for our first particle, so velocity of particle 1, it's going to be negative 2 pi over t times our amplitude, which is a over 2, sine of our 2 pi, our time was 0.5 seconds, our period is 1.5, and when we solve for that, we get that the velocity is negative 0.866 pi a over t. And then our velocity for our second particle is going to be negative 2 pi over t times our amplitude sine 2 pi times 0.5 seconds over our period of 1.5 plus pi over 6, which gives a value of negative 0.5 pi a over t. And since both velocities are negative, that means that they are moving in the same direction.